Okay, derivative formulas in 2.5. First of all, let's think about a linear function. So if we have f of x equals mx plus b, nice linear function here, the graph here is going to be some sort of line, all right, where the slope is m and the y-intercept is b. So if we're thinking about a line and we're thinking about derivatives, the derivative is going to be a line that's tangent to the graph. So in this case, when we're looking at a straight line, any line that's tangent to this is also going to be right along that same line. Therefore, the derivative of a linear function is always just going to be whatever m is. Now, if we look at a constant function, it's the same sort of idea, except for this time it's going to be a horizontal line going across. In this case, if g of x equals 5, it's going to be going straight across, left to right, at a y value of 5. Now, we can rewrite this as mx plus b if we think 0 x's plus 5. All right, therefore, we can kind of use that same rule that we just thought about with linear functions. In this case, a constant is always going to be 0 for its derivative. Now, things change a little bit if we think about the x squared. All right, the x squared graph is a parabola kind of looking like this. All right, now normally this would be at the origin for its vertex, but if we think about tangent lines to the curve, tangent lines are going to have different slopes depending on where we place them along this curve. All right, so it's going to change. It's not going to be a constant every single time. So to calculate the derivative here, one way we could do this is we could use the limit definition of derivative. So to calculate h prime of x, well, we could fill in, we could look at the limit as h approaches 0, and we'll plug in x plus h first. So x plus h goes into the function minus the function itself, all divided by h. This is going to take a little bit of time to simplify down, but what we'll do is go ahead and expand that out. So the limit as h approaches 0. I'm going to visualize it as 2 copies of x plus h multiplied together. Then we're going to go ahead and distribute that. So the limit as h approaches 0, it'll be x squared plus 2xh plus h squared minus x squared, bringing that along, all divided by h. A little bit sloppy. Takes a little bit of time combining some like terms, or x squareds combined together as their like terms, get to cancel out, making 0 x squareds. So now we're to the place where we have the limit as h approaches 0. What will remain is that 2xh plus h squared. We could factor out an h from each one of those terms, leaving us with 2x plus 1h. Why we would want to factor that out is so we can simplify this down to lowest terms, removing this h between numerator and denominator. And at this point, we have the limit as h approaches 0 of 2x plus h. We no longer have that problem with dividing by 0 if we plug in 0 for h. So replacing h with 0, our derivative is going to be 2x. All right, that is a long process to get to our derivative. It's important we understand how to use the limit definition of derivative, but there are shorter, faster ways. That's what we're getting to next. Is we're going to introduce the power rule, the constant rule, and the linear function, how to take those derivatives. So that's coming up next.